This work I would like to present today is decentralized application level adaptive scheduling for multi-instance DNNs on open mobile devices. Here is the multi-instance DNN situations on the mobile devices. And then the open, we means here is user could implement and install their own applications here. Like the figure on the right top, we can see the people can implement and build their own DNNs applications. Also, there are lots of famous and frequently used applications such as TikTok, Twitter, Instagram, and YouTube inside a single mobile environment. And those applications may be implemented and installed by the user themselves, so each mobile is unique, their environment is special. And all of these applications will integrate DNNs inside it in the near future because the emerging of the AI. However, in this kind of mobile environment, we could meet these four big issues. Limited resources, more specifically, the situation we discuss here is edge computing. All the computation is not relied on cloud, only device computability itself. The second one is heterogeneous code assignment. Due to the AI demanding, there are more and more specialized hardware pop out, but regular processing like CPU, GPU still remain. How these processing units can fully utilize in this kind of environment is a big issue. And here comes to the third point. If you do not assign those top applications properly, their performance will be degraded. We would imagine this situation like audience to compete one single GPU at the mobile, but leave the other like special hardware alone. So, and definitely it will be slow down everything. The fourth point is the privacy on each app. Most of the app would ask you to this annoying question. When you install it, do you allow the apps track your data from the another apps? Then not all users or not all apps wanted to allow the other apps to track their data. And we can look closer on the performance issue. And here's the standalone profiling for 3 DNN networks. We've profiled the standalone average power and inference time for different DNNs in the different resource constraints. And the thread I means the model is executed on CPU with a number of I threads. NAPI, low power and fast single answer are 2 options that TF-Lite model code generation that consider using GPU or any other accelerators. Even though they are not co-running at the same time, they have their own best option. We can see on the figure, the different DNNs have their own best option for their configurations. Users may need to spend the time to profile it and to make a best decision for each different DNNs. So the main aspect of the scheduling focus in this work is the execution configuration that affect the user computing units, which is essential for performance and power consumption of the DNNs. The relevant factor includes some that are controllable at the application level and some at the OS level. So DNN right in TF-Lite is what we focus, and the application can explicitly specify whatever the DNN should be run on CPU or accelerator, for example GPU, and the number of CPU threads to use. It may also call apps in the NAPI, whether the performance mode or efficiency mode. So the API will automatically determine the CPU accelerator to be used for DNNs. We uniformly regard such configuration as application level controllable configuration, which is different from the OS level scheduling. When the DNNs run on certain configuration, the OS may exert further influence on the usage of computing units. For instance, if the application level control set the DNN to run on CPU with 2 CPU threads, the operating system will ultimately determine which 2 CPU cores a thread will run on. And we design our solution with the following principle to respond our motivation. The first is the scheduling should be decentralized for each app. This is because most of the relevant factors inside the app and the app level should be easier adopted as they do not need to change under their underlying different kind of OS version. And the second is the scheduling should be able to adapt to the influence under the OS level and the other all environment factors. The third is the scheduler should work efficiently, adapt change in the system as soon as possible. And here is the more formal problem definition. I think we listed on the paper. So I just briefly introduce it. We were given a set of the application and execute them on the device V, and some of them are maybe run at the same time, and then all the application will in the set A, and then they have their own DNNs, and then they employ some policy P to decide the execution configuration of each their own DNNs. And then our objective is to find the policy such that will minimize all the energy consumption and the latency time multiply as small as possible. And the constraint here we set is that the scheduling policy P in the apps cannot access the information from the other apps due to the isolation enforced by our setting. The second is each app priority and temporal scheduling are controlled by the underlying OS. Okay, and here comes our first research question. How can the scheduler work efficiently without directly knowledge of other apps? Many offline algorithms may help solve such kind of optimization problem, like genetic algorithm and so on. Typically, we could separate those learning algorithms into 2 categories, supervised and unsupervised. They have their own benefits and drawbacks. For the supervised learning, the first one is they require offline labeling and training. And then the second is adaptive slow. But the benefit is that they can lightweight it and compute more faster if you have highly optimization process. And the second for the supervised learning, the first one is no offline. The benefit is that they do not need to offline learning and they can do the adaptive, but the drawback is they are heavy and computation intensive. But however, our discussion is for the online multi-tenant scenario, where ideally learning-based, adaptive, and lightweight algorithm is more preferable. So those two categories cannot satisfy our situation. And then additionally, the apps on the smartphone may be developed by many competitions such as Twitter or Meta. And for security and privacy, open mobile system requires strong isolation among those apps. That is, one app cannot and should not access the direct information of another apps. How can scheduler work well under such strong constraint? Is one of our research questions. And then thus our design in this app is adopt semi-supervised deep reinforced learning based algorithm. More specifically, we adapt deep reinforced learning network as a semi-supervised method. It requires no manual label, but active explore environment and learning from the relation between the action and reward automatically. The learning model is predict the next suitable action, which is configuration. And this in nature make it good fit to the dynamic environment in our problem. Also, typically, the model of the DQN could be lightweighted, like 2 to 5 fully connected layers. And here is our figure of the structure of our decentralized DQN scheduler design. And the figure shows 3, in this figure, but it only shows 3, but you can imagine it can be more. So these 3 controllable DNN applications, and they have their own reinforcement learning agent, and they will select the corresponding action. The action means which different kind of code generation or configurations. Its method is satisfied the isolate environment because each controllable application will not depend on any information directly from other application. And also we include some corresponding uncontrollable apps like the web browser, YouTube, and TikTok. And then we say they are uncontrollable axes because they do not contain our reinforcement learning agent inside. And then the application, and the action in each app could be different. So that is the flexibility that offer the user, they can design their own action in their own application. We test those basic configuration to generate corresponding codes in our paper. However, we could imagine that each application could have different code generation design and not required to follow our papers. And in this paper, we consider 2 major concerns of the DNN running on the mobile device. The first one is latency. The agent will consider end-to-end inference time for the DNN model with selected action. And on the other hand, the power consumption, we use the operating system give battery measurement tool to monitor the energy consumption after each inference. We would like to find the sweet point between these 2 metrics under corresponding status. The detail of reward function we use in this paper is in this formula. Where LSAI represent the latency of the inference of the DNNI, which with action on the status S. Status means the whole environment situation given from the OS operating system. And WAI is the average power of the inference of the DNNI with action A, and DI is the deadline of the inference DNNs. And here comes to the second research question is how our user level solution deal with the effect with the scheduler under the underlying operating system. The OS influence in the execution of the app OS will allocate the computing units and other resources to each app and determine when an app runs and their priority level. And the OS scheduler is different from one version of OS from the other. So we avoid demanding change the underlying OS to let it upgrade or into another version. So the US level deep reinforcement learning scheduling will adapt and interactive with different kind of OS. We will see the OS as an environment changing. Also, each agent can have their own flexibility to handle some private feature which do not want it to share with the OS because the application and the OS company will may be different. Yeah, and here comes the third research question is can the decentralized scheduling cover to a good result? And on the open mobile system, apps comes and goes, and the workload on the system may be various. So without the knowledge of other co-running app, can decentralized scheduling cover to a good resource? In this paper, we review some previous paper that would like to prove the multi-tenant schedule situation can be find a global optimal solution. However, they have proved that it's NP hard problem. Our consideration is to make each agent converge as soon as possible, not pursue the global optimal. Thus, we consider the whole system reach the Nash equilibrium, which means stable systems. So we empirically show our design could meet to the stable and good enough result as soon as possible. And here comes to our evaluations. So here is the software we use, software and hardware we use in this paper. And the left-hand side, left-hand side is the mobile phone environment, which we use the Galaxy S21, which have for their Android 12 OS, and then they have Snapdragon SoC, which include the 8-core CPU and 1 GPU and 1 DSP. And then the right-hand side is the tablet environment, which also mobile devices. And they have the same operating system, but their system on chip is more advanced, one level. So I think the difference is the compatibility is different. And here, this is the DNNs we implement in our testing, our evaluation. We have 3 groups of the DNNs, and which each of them are the models inside have 3 kind of different kind of DNNs. And then the right-hand side is the standalone is offline profiling for each kind of DNNs on the tablet and the corresponding phones. Okay, and here comes to the first experiments. Co-run 3. In this experiment, we co-run 3 DNS groups with uncontrollable. And this is the 3 the profiling the experiments on the phone, and then we can see the comparison of these 2, and then these 3 comparisons are the first 2 are the DNs in the group always using the 2 setting of the NN API, and the best standalone action is what we do the offline profiling to find the best performance when the DNNs run standalone in a specific device setting. Actually, the best comparison in this is the Oracle result, which is testing all the combination of all the setting and the DNNs. However, we regard finding the Oracle result is an NP hard problem, so we do not do that. So instead, we use some static setting or simple profiling method as our comparison. So we can see the best standalone method meant the huge performance degradation on group 1 single post DNS. That is because it could not foresee the co-running situation on the offline profiling. And the NN APIs met a similar problem as well. This situation happened at the group 2 at the YAM-net. Even though they could do code generation with low power mode, they still could not predict how co-run will affect the DNS running on the running time. These 2 figures are the same experiment but on the tablet. And because the SoC of the mobile and tablet device, which have 1 generation difference, the performance showed a slight difference as well. But we could see the NN API could have better performance, even matter performance degradation. We guess that it is because the new SoC have larger bandwidth, could handle more corresponding kernels. However, no matter which version devices or group of DNNs, our decentralized DNN perform better than all other comparison. And here is another research question is that how machine learning-based decision model take time to learn, but the dynamic nature of the mobile system demand fast response. Can decentralized scheduling match the the converge speed they need? And this figure shows the reward converge trend of the 3Fs in the group 2s. So each report DQN's normalized reward trend to prove the DQN converge in different situations. Each figure is mapping to use each DNN in group 2 and place each DNNs in foregrounds. And the situation we see here is that no matter what situation or environment is changing, the decentralized DQN still go to stabilize after maybe 600 runs. That's what reach the stable systems. And then here's another experience we made. Okay, and a stable our method. In figure 5, we show the early stage each marble could affect the configuration randomly. However, after 400 rounds, they continue to be stable. And then the final research question we would like to answer: can this solution work with the uncontrolled apps such as TikToks? And here we can see the environment is that three DNNs controllable application running on the background and the TikTok running on the foreground. And then we can see our master still can handle this kind of dynamic environment and then let those perform better. Okay, and then the overall contribution of this work is that I think this is the first decentralized application level adaptive scheduling for multi-instance DNNs, and then we can guarantee their private edge apps privacy and make the performance maintain well, and then that is our the conclusion of our apps. Thank you very much.